Hi, my name is Anders Hjermestad. I work as a consultant at the Danish Technological Institute. In this course, we will look at powder bed fusion in metal. Here there's a slide about the 7 technologies in additive manufacturing. And today we're going to look at powder bed fusion in metals, which includes the 2 technologies, DMLS, direct metal laser sintering, also known as selective laser melting, and the technology EBM, electronic beam melting. So, according to the ISO standard, it is a metallic process that is melted and the material feedstock is powder in a powder bed where a selective fusion of the material occurs. Therefore, the name powder bed fusion. And the heat source to melt the material can be either an electron beam or a laser. Let us take a deeper look on the technology. So, the selective laser melting has the following components. It has a build chamber that you of course build in. Then there has a laser, and it could be more lasers. Then there are mirrors that reflects the laser. We have a recoater that distribute the powder from the powder bins. And then finally we have a heated platform. Now let's take a deeper look at the process. First we heat up the platform that we're building on. Then we're ready to print. Then we lay a thin layer of powder on top of the platform, and then the laser is running over the platform in a pattern that you would like to print. Then you lower the platform, and then a powder layer is distributed on top of that, and then this process just continues until you have a final part, and then we have a cool down of the process, and after that the process is ready to be unpacked. Now let's take a look at an actual printer. So the first thing that you see here is the recoater distributing a powder layer on top of the last layer. And after that, you can now see that the laser is running in a pattern forming the part. And all the spots that the laser hits melts the material and form the part, while the rest of the powder can be reused after the process. So now the laser is finished, and a new layer is distributed on top of that. So the next process is quite similar. It's called electron beam melting. So in this we have a vacuum build chamber, and instead of a laser we have an electron beam and electromagnet that guiding that beam instead of mirrors. But we have same recoater and the same powder bin system. And for this process you heat up the whole chamber instead of just the platform. And let's have a look at the process flow. So the first thing is that you heat up the whole chamber, and then you are ready to start printing. And then, as the SLM process, a recoater distributes a layer of powder, and you have a constant heat of that chamber. And then the electron beam melts the part, similar to the laser. And then you lower the platform, and then this process continues to occur until you have a finished part. And then you have a long cooling period, typically a couple of days. And after that, you're ready to unpack the parts. And a comparison of the 2 technologies. So on the left side, we have the SLM technologies that is good for producing parts with low surface roughness and parts that have higher degree of detail level. And many materials are available for that technology. On the other hand, we have the EBM technology that uses less support and can be a large, thin structure without warping these structures. Of these 2 technologies, SLM is by far the most industrialized. Therefore, this course will focus on the SLM technology. So a comparison of a low-cost printer versus an industrial printer. So on the left side, you see a lab-scale printer, and on the right side, you see a large industrial printer. Typically, the industrial printer like this one is a factor of 10 more expensive than the lab scale printer. But it also prints a lot faster, typically a factor of 20 of these 2 printers. And you can print bigger parts. Next up, we're gonna look at pros and cons for the technology. When you should choose an additive manufacturing technology, typically you can choose from either a visual appearance or a functional of the part. The SLM process is definitely only on the functional parts, as it has the highest mechanical strength. It has the best tolerances, and it is resistant to chemical and heat, and it is biocompatible. So for SLM parts, the material properties are good. The values are listed here, and as you can see, there are very high tensile strength, decent elongation, and these are typically valued for titanium. So all these values are validated after each build of a critical part, where tensile bars are placed on the platform. So the main benefit with this technology, SLM, is that it can be used to produce end components. An example is this pulley wheel that is used on bicycles to guide the chain around. And to prove the quality, this one has actually been used in the Tour de France. The technology SLM is mainly for industrial use. Here is an example of a machine from SLM Solution that has one of the largest build chamber. And typically a full build chamber can take multiple days. The dimensions are fairly large. These machines are the size of a normal CNC machines. Prices are typically about 1 million euros. And that is only for the printer. One of the downside with the technology SLM is that the surface can be quite grainy and matte. You can see values on the right side. These surfaces can, however, be post-processed to a lower RA value with either polishing, blasting, deburring, machining, etc. So SLM printing is a fairly slow technology for producing prototypes compared to other technologies as FDM. But it is fairly fast to produce small and medium-sized batches. Here you see an example of producing a platform of pulley wheels. First there is a heat-up period, and then there is a print time period. So print time will of course depend on the specific part or platform you're printing. For this specific platform it will be 16 hours. After that there's a cool down period and an unpacking period. Typically it takes 1 to 2 hours. Then there are heat treatment, and this is of course dependent on what kind of material properties you're looking for. In this specific platform it will be 5 hours, and then there's a final step with support removal that again can take 1 or 2 hours, or it could take even 12 hours. To sum up the pros and cons for the process. In general, there are good mechanical properties. It is ideal for functional parts and prototypes. Complex geometry can be designed and produced fairly easy. It has high strength. Many different materials are available. And it is excellent for small to medium batch production. And it is a reliable process. Some of the downside, it is an expensive process compared to conventional manufacturing. Tolerances are not as good as conventional manufacturing as CNC machining. SLM systems are mainly for industrial use, and there can be somewhat long lead time on prototypes. The surface can be grainy. It has a shrinkage of 3 to 4%, but that can be compensated for. It is prone to warping in large flat areas. And finally, we have high stresses, and this is why we have heat treatment afterwards. So next up is design possibilities. So the first possibility is to create internal channels. Here is an example of an internal channel. They need to have a minimum diameter of around 1 millimeter, so you can get the powder out of the part afterwards. But it is of course dependent on the length of the channel and also the design. It can also create lighter structure. Here is an example of a tool that is conventional manufacturing on the left side, and then by SLM on the right side. And on the right side you can see it has a lattice structure where a lot of material has been removed, so it is a lot lighter than before. Hollow structures can also be created. Here is an example of the pulley wheel that we saw earlier. So it has an internal cavity all the way around, and it has small holes so you can get the powder out of the part. And this also makes this pulley wheel a lot lighter. Also, part can be consolidated, meaning that a lot of component in an assembly can be consolidated to maybe 1 or 2 components. Here's an example from the food industry. Before it had 42 components and 45 assemblies machined in 316L and weighed about 600 grams. After they have designed it for AM, it consists of just 1 component, but with 6 assemblies and a weight of only 250 grams and around the same price as before. So the benefit is that it is lighter meaning that it can move faster and producing more. And it also is a lot easier to clean, and it is faster to assembly. And here we can see the supporting element in action. To sum up the general design possibilities with the technology, you can create flow channels, meaning more efficient cooling or thermal properties. You can create lattice structure, you can create new functionalities, and in general, these components can be created with a lightweight. And finally, you can consolidate parts. Next, we have design guidelines. So I'll talk about 4 specific topics that you should be aware of when you are designing parts. So we have support and overhangs, meaning that all kind of overhangs need support structure. We have embossed and engraved details, and we have escape holes to empty the parts for powder. And finally, we have tolerances. So first up, we have support and overhang. A typical rule is that if you have an angle below 45 degrees, that surface needs to have support. But a bit below 45 degrees can be acceptable, but you will have a very grainy surface, and if you're going too low, the whole part will collapse. On the right side, you see a typical example of a part with support structure, where you have support structure all over the part. So this is a specific topic that these machine vendors are looking at. Be able to print parts which has overhang down to 10 degrees without support. It is possible to emboss or engrave details on part, meaning that if you want a serial number, you can have that on the part. It is recommended to have either 1 millimeter height or depth for that detail. For escape holes and channels, it is recommended to have a hole size of minimum 5 millimeter. It can, however, be a bit lower if you're just going for a straight line. When designing these channels, it is important to have curves rather than just have straight lines and 90-degree angles as the design you see to the left. Because in these 90-degree angles, the powder can get stuck and it can be difficult to blow out the powder with compressed air. So rather go for a design in number 3 or 4 in this figure. Next up is tolerances. The standard tolerances are 0.1 millimeter. But it is of course dependent on the part geometry. There are some specific designs that you should pay attention to that have negatively influence on the tolerances. Try to avoid having large flat surfaces and thin walls, and trying to avoid abrupt changes in cross-section areas as it will distort the part. And also pay attention to holes printed in the XY direction. They will be elongated. So pay attention to how you orient the part, as it will affect the tolerances of the part. So the reason why we have all these design rules is basically to ensure that the part that you're designing is also the part that you're getting out of the printer every single time. You could of course try to push the limit of these rules, but it will come with a risk that the part will not be perfect. So next we have materials for the process. So here we see the main categories of the alloys that are used in 2021. And please pay attention to that we have a rapid development in materials for AM. So each year there come new materials. But we have, first of all, the aluminum, which is very common. It is good for cooling and lightweight, and it's also the cheapest material. We have stainless steel, good for end component. Generally, it has high strength. It is well known in the industry. We also have titanium, one of the biggest material. It is good for high strength combined with low weight. And then we have tool steel and various alloys of that in general use for tools that require high hardness. And then we have the cobalt chrome, which is specific for the dental industry. And then another big one is nickel-based alloys. This is a super alloy used for high temperature application. Also here we see various alloys of that, specifically the Inconel and Hastelloy is big one for that. And then finally we have copper, used for only good heat transfer. And there is of course pure copper and then some kind of alloy of that copper. For all these categories there are many different alloys that suit the specific need that a part will have. Let's have a look at what we can print with SLM. First we have a case from Bühler Meinecke, with an extrusion nozzle that I use to extrude cookie dough. They used to be made in brass and then brazed together by hand. Now the process is automated and it is printed directly in one component in either stainless steel or titanium. So this graph is comparing the economy for 3D printing versus conventional manufacturing. And we can see for this specific component there are a lot of advantages. So they're starting from the left. It has more design freedom, meaning that you can have the geometry that you actually want. And then looking at the production, we now have a faster production. It is more easy to create the identical geometry that you're designing because you don't have this hand process. We also have lower cost of producing the component. And finally, we have higher durability due to the new material that we're using. So next up is an assembly aid used to centering a compressor stator. And you can see the conventional design and then the new design with a lattice structure. And in the table, you can see there are both savings in terms of lead time, but also cost. And let's have a deeper look at that on the graph again. So in the development phase, you can now have more design freedom, meaning that you can have the part that you actually want. But on the other hand, you need now to create this lattice structure, which requires more time. In actual production, the part is slightly more expensive to produce with AM, but it has higher durability due to the new material that we're using, meaning that the annual cost will be lower because you don't have to scrap the part so fast. An important benefit for the daily use and the operator is that the component now has a lower weight. This is important because the operator needs to lift this tool many times each day. So the final case is a burner nozzle from Siemens Industrial Turbo Machinery. It has a conventional design where it has 13 machine parts joined by 18 welds, and now they are able to produce it at just one part, which has optimized performance because it has more optimized cooling, and it also have additional benefits. It has significant less lead time, and it is also lighter. Let us take a look at the chart for the economy for this part. As the other part, this one has more design freedom, so it is possible to make an even more optimized design than before, getting better performance. A small downside is the certification of this one, which is still a bit time consuming for critical parts of AM. On the production side, this one needs no assembly tools. It is cheaper to manufacture, and the most important one for this one, it has better performance. So just a small percentage in better performance has a huge impact in the lifetime of this component. And it actually also have higher durability because it has no assembly, no welding lines and stuff like that. Let's look at health, safety and environment. When working with SLM and EBM, it is important to have the right safety equipment. Both processes are using powder with a grain size less than 100 microns, meaning that you should wear face mask with the P3 filters, recommending gloves, goggles, working clothes in general, and safety shoes. Taking a deeper look into the safety, it is important to notice that the powder itself is not approved for food, drink, or medical application on the human body. However, printed parts can be approved for these applications. All powder, and especially titanium powder, is flammable and can explode. So in the production, the amount of loose powder should be kept at a minimum. Regarding fire and explosion, ATEX workplace evaluation is mandatory in Denmark and must be renewed with changes in the production, or minimum every third year. The ATEX work evaluation looks into the possibility of explosion when you're handling powder and other explosion risk materials. So next up, we will look at the printing process in more details. So I have selected this part to go through all the production steps. And the first step to do is to have a product specification on that component. And that could be, for instance, what is the characteristics of that part, the functionality of that part, and what is the performance. All these specifications are then gathered in a document as the one that you're seeing to the right. So first, there are some requirements to the alloy that you're printing in. For this one, it is titanium. There are also some requirements to the mechanical properties, which tells you something about post-processing, like this one should be stress-relieved heat treatment. That could also be requirements to the chemical composition, and one of the more common, geometrical tolerances. There are typically a technical drawing to that component. And then finally the surface roughness, which determines what kind of post-processing is required for this part. First up, in print job preparation, we will look at the orientation of the part. And it is a compromise between different parameters to have the right orientation. You would like to minimizing the amount of support that is needed to print the part. You'll try to minimizing residual stresses when you're printing the part. You want to optimize the nesting of parts, meaning you would like to print as many as possible parts in the same build job. And if you have important details or features, they should be placed facing upwards to get the highest resolution. As mentioned earlier, support structure is needed in SLM. And this support structure is used to keep the part attached to the platform during the building. And at the same time, this support structure should be accessible and easy to remove after the process. So this support structure is something that you add in the preparation step. Next, we have nesting of parts. And in a normal situation, you just want to print as many as possible parts. But for a serial production, you will go through the following steps. First, you will have a qualification build, like the one you're seeing to the left, where you have tensile bars and you have artifacts. These specimens and artifacts are used to ensure that you fulfill the product specification. After you fulfill this, you're ready to go into production and produce the one that you're seeing to the right, where you just have one tensile bar. This tensile bar is used to have continuously build control. So we looked at the printing process itself in a previous chapter. Here is a slide about all the equipment that you need for printing. To the right, we have the printer itself, and after each build job, you will remove the build platform to station 4 to the left, which is a powder removal station. At that station, you can vacuum all the loose powder that you didn't print in, and that powder goes then to the powder sieving unit, which is number 3, and that sieves all the powder, and all powder can be reused after that. Next up is post-processing. This video shows some of the steps in the post-processing. So here you see the part being printed in the printer, and just after it is finished, the platform is lowered, and the platform is now taken out of the printer and placed in the powder removing station. And the powder is now being vacuumed away from the platform. Now all the powder is removed, and the platform can be removed to stress relief. Here is placed inside a box that is first vacuumed, and then it is filled with protection gas. After heat treatment, the platform is placed in a bandsaw, and the parts are removed from the platform. And now you see a removal of the support structure and a glass bead blasting. And finally, we have a deburring step. So let's take a look at all the steps individually and start with heat treatment. So heat treatment is first of all used to remove residual stresses. This is specifically relevant in AM where these stresses can be high. In general, you want to optimize the mechanical properties. And that could be to have a more ductile microstructure, but it could also be to have a more isotropic microstructure. There could also be more specific needs that you're looking for. One of the more common is to remove porosities with a hot isostatic pressure known as HIP. This is specifically relevant for highly critical parts like aircraft component. It could also be to softening or hardening the component. This is relevant for tool application and tool steel. Finally, it could also be used to improve corrosion resistance, which is relevant for typically stainless steel, but also nickel-based superalloys. Then the support should be removed. First, you want to remove the part from the platform, and that can be done by either EDM or a bandsaw. So EDM is for more gentle removal of the part, while a bandsaw is fast and cheap. Basic tools are then used to remove the light support structure that you have, and this can be done by either gripper, screwdriver, or a hammer. For the more heavy support structure, you need also heavy tools. That could be an angular grinder or a column drill. Next is deburring. So different kinds of grinding chips are used for different materials. And what they are doing is they are smoothing the outer surface. But pay attention to that these chips can't go into channels, small holes, and sharp corners. Below you can see typically value for as printed and deburred surfaces. In the bottom right you see an as printed surface of 316L stainless steel, and you see a deburred surface after 2 hours. And what you see on the deburred surface is that all the tops are grinded away. So after deburring we have abrasive blasting, and that can be done with different kinds of media. The two most common are corundum and glass bead. So corundum beads are angular particles which cut through the surface and remove some of the surface, while the glass beads are round particles and they make a more even and peened surface on the part. On the lower right corner you see an as printed surface of, again, 316L stainless steel, and you see a surface that is blasted by corundum and glass bead, and again you see a more even surface than compared to the as printed surface. In addition to the common post-processing, there are also specific processes that can be designed for specific needs. This can be either electropolishing, where you will achieve a mirror-like surface, like the one you see on the upper right. It could also be abrasive flow machining that can be used to create smooth internal channels. Finally, you can use PVD coating to achieve a very high surface hardness. Next up is quality assurance for SLM and EBM. Today we already have a specific standard for metal AM. Here are two examples for metal AM of titanium and one for aluminum alloys. More information about these ISO standards can be found on the link below. Samples and artifacts can be used to control the quality of the build job. Here are some of the artifacts and samples that can be used to validate that. On the upper left you see a tensile bar that are used to validate mechanical properties in general. You can also design specific artifacts that represent some specific feature on the part, like the one you see on the upper right, where artifact is used to validate the bending strength of that component. On the lower left you see smaller details, which are then used to validate that you can print these details. On the lower right you see a reference artifact, which is an ISO artifact used to validate geometric tolerances. So data from the machines can also be used to have inline quality control. All modern systems have a lot of sensors. You see an example of that to the right, where all kind of sensors are listed. These are both temperature sensor, but also sensor for the gas flow and the oxygen level. For instance, oxygen has to be below 0.2 during the build job, because a too high degree of oxygen will result in a lower quality of part. On the lower left you see a graph of the oxygen, and you can see that the oxygen during the build job has never been above 0.1. This will mean that this build job is approved and there are no red flags for this. Finally, we have some links and references for further reading. This includes general links about AM and magazine and publication, as well as SLM and E-beam related links.